All right, in this example, we have a compute a triple integral over, of z. So we will be integrating something of the form over w, which we have not yet written, which we will write soon, of the function z dv over this region w. So this region w, we can go ahead and work on sketching it here. So for w, we want to be within the cylinder. So what I can do is create a, let's go ahead and look at this inequality here. We want specifically where z is between 0 and y. So let's go ahead and actually sketch the graph of z equals 0 and the graph of z equals y, each of which are planes. So z equals 0, we have the xy plane itself, and for z equals y, we have this slanted plane. Okay, so that's what we have. And now we also want to be within the cylinder. And this is a cylinder of radius 2 centered at the origin. So we can go ahead and graph that as well. This would be an implicit surface. So we can do x squared plus y squared equal, we'll do equals 4 for the moment. So equals 4 will give us that. Okay. So because of this inequality, this is really saying we only want to be within the cylinder. So if x squared plus y squared exactly equals 4, then that's why we have this. But if we made it an inequality, this would fill it in. So we want not just the surface of the cylinder, but also the interior of the cylinder, but only the portion for which every z value is between these two surfaces. So effectively, we're only interested in this portion right in here that's being clipped off. So there's another feature of Calcplot 3D where we can go ahead and take a look at that in more detail here. So let's look at that. And if we look at this, we can see the full thing. So this is where I typed in everything, but we can also add to this a region. So a region is what Calcplot 3D enables us to section off a three-dimensional region. So for the region, we know that the bottom is f of xy, which is z. We know z equals 0 is the bottom. We know the top of the region would actually be this plane, z equals y. So we'll just make that y. We also know that because we are within the cylinder, we know that if we view this in the xy plane, let's go ahead and look at this in the xy plane. So here's the xy plane. Z is coming out of the screen. Let's go ahead and kill that plane for a second so we can just see the cylinder, which really its trace in the xy plane is a circle. So we know that the x values go from -2 to 2. -2 to 2. And the bottom, well, what's the lowest y value? Well, really this plane actually does cut things off because we are only interested in the area, the volume between. Where this plane, z equals y, hits the xy plane, it hits it at right here, which is actually the x-axis itself, which is y equals 0. So we're going to go ahead and make y equals 0, the bottom, and the top would actually be the top half of this cylinder. So we take the equation of our cylinder, which got a little cut off here, but we take this, set it equal to 4, and solve for y, and we take the positive root. So if we go ahead and do that and solve that for y, we should have positive, since we want the top half, square root of 4 minus x squared. So now let's actually go ahead and delete the surfaces here. And now we can actually see our region perfectly is that little wedge. So that is exactly what we are going to be integrating over, that three-dimensional volume right there. Okay, so we can think about this. We kind of actually have everything set up based on this region here. This region tool is great for visualizing triple integrals because we now know what the top and bottom functions are in the z direction. So right here we have our top and bottom bounds for our innermost integral. So immediately we can go ahead and write this. Let's go ahead and get rid of this graph for the time being. And we can go ahead and write this as we'll do this in stages, so I'll leave a little room here, but effectively we know that the top surface is z equals y, and the bottom surface is z equals 0. Our function we're integrating is z, and then we'll have, for cylindrical, we'll have our dv for cylindrical. So let's remind ourselves what that is. For cylindrical, dv is r dz dr d theta. So we'll have r dz, and then we'll have dr d theta. So now we need to have r bounds here and theta bounds here. So for the time being, let's just say this is well, we can section this off for a moment. So we'll just pause. So let's remind ourselves, what actually is D? So D is what we get when we take this region here and we project it into the xy plane. So if we look above the xy plane with the z-axis coming out of the board, we would see something like this, which actually is simply that cylinder. It's the upper half of the circle that we solved for. So it's actually, this is our outer boundary. This is the bottom bound. So if we think of this as living in the xy plane, how would we describe this in a radially simple manner? Well, clearly theta goes from an angle of 0 all the way around to an angle of pi. So we can go ahead and update our theta bounds 0 to pi. And since our region here actually touches the origin, we know that the r bound, the lower bound, will start at 0. And then what's the farthest away we go? We go to this curve. Well, every single point on this curve is the same distance away from the origin, since it's part of a semicircle. What's that distance? Well, 2. So every single point on this circular arc is a distance of 2. Therefore, the radius is just 2 for the upper bound. So we can go ahead and erase that stuff. And this is our triple integral in cylindrical coordinates. We don't have to do any conversion of our integrand function because in cylindrical coordinates only x and y change to r cosine theta and r sine theta respectively. Otherwise, they stay the same. So we can integrate this pretty easily. We'll go ahead and actually, I just talked about how we have to change. You're right, we're correct. We do not have to change the integrand, but this upper bound here of y, this definitely needs to change. So let's actually go ahead and take that y away and remind ourselves that in cylindrical and polar, y is r sine theta. So this is actually going to be an r sine theta. Now we're ready to integrate. So First, we'll integrate with respect to z to get a 1/2 z squared between 0 and r sine of theta, r dr d theta. And then we can go ahead, pull out the 1/2, 0 to pi, 0 to 2. And if we square this upper bound, we'll have r squared sine squared. So we'll have r squared sine squared theta, and we'll subtract 0 squared, so we just get the same thing. But then we have to multiply this by that. So we really have two r's here and an r there. We can combine them to actually make this an r cubed. So r cubed sine squared theta dr d theta. Important thing to note here, because these bounds are all constants, and we can write our integrand as a product of something only containing r's, that's over here, and something only containing thetas, that's over here, we can actually split this up into the product of two different integrals, a d theta integral and a dr integral. Do you have to do that? Absolutely not. Some people, though, find it a little bit easier to work with, so you are free to do that. And you get something that looks like that. Now for this sine squared theta, to integrate that, we're going to use a half angle identity. So sine squared of theta is 1 minus the cosine of 2 theta all over 2. So if we do this replacement, we can take the 1/2 here and here to make a 1/4, which we'll get. And then when we integrate this piece, we'll get a 1/4 r to the 4th, which will then multiply in the very next step with this 1/4 to get a 1/16. Okay, so really we only integrated this integral this time because we needed to rewrite this integral using this half angle identity to get here. So with that, we now can pull out and combine the 1/4 to get a 1/16. We'll integrate this to get theta minus a half sine of 2 theta between 0 and pi. And here, this will give us, well, what is 2 to the 4th? 2 to the 4th is 16 minus 0. So the 16s will cancel, and then we'll be just left over with, well, whatever this evaluates at over pi and 0. If we plug in 0, this becomes 0, sine of 0 is 0, so we only have to worry about plugging in pi. Plugging in pi into sine, any whole number multiple of pi, sine of that is 0. So this whole thing just becomes pi. So the 16s cancel, and we'll have pi.